There it goes.
I never tried
Oh. I don't know who that is. Actually.
Well, everybody, welcome. Thanks for turning out on this beautiful afternoon. Look at the crowd you drew. I am pleased to introduce to you Ben Gobler, who's going to tell us about two geometric riddles.
Thank you very much. It is my pleasure to be back. Last year we talked about the mathematics of tangling ropes. So I just love these kinds of physical, tangible, geometrical, kinds of like recreational puzzles. So today I'm bringing you two of my favorites. I'm somewhat of a collector, and so yes, so for today, let's split the time and enjoy these two geometric riddles. So let's begin. And so I just make sure this is okay. Great. Okay. Yeah, so we'll begin the first one by looking at some art. This is a recognizable piece. It's The Last Supper, from the Renaissance. And what's notable about this painting and other paintings from the time is that they're drawn to look 3D. So they have perspective, and that was new at the time. And to give you a sense of how this is achieved, I want to highlight some lines in the painting. These are some of the lines that appear that in the room are supposed to be running front to back. So these are the lines that are going into and out of the painting. And it's a little bit of an optical illusion, but if you extend all these lines, turns out they actually meet at a point, which maybe it didn't look like that was going to be the case, but it is. And actually, if you zoom in and look a little bit closer, you'll see that the point where they meet is somewhere here on the horizon. So look out the window, and you can see that the meeting point there on the mountain's edge. And that's not a coincidence. That's the technique that's being used to achieve this perspective drawing, 3D perspective drawing. I found another example. This painting is from maybe 10 years before. And we see it's like a plaza, and there's a grid of tiles on the ground, which is made out of, it has these same types of lines. So let me highlight the lines that are running forward and backward. And this one I find really surprising, because if you look at some of the ones that are far away, let me hide the green lines. You see the lines that are all the way out here on the bottom, they look like if you extended them, they might go off into the sky. You agree? It's hard to tell, but I've done this with the computer, so I can show you what happens if you accurately extend those lines, and you find they actually meet at a point. It's incredible, and again, it's somewhere there on the mountain, on the horizon. So think of the technique you can use to achieve that three-dimensional look. But the more interesting point to make here is about the other lines, not the vertical running lines, but the horizontal lines. Let me highlight those. These are the horizontal lines, and unlike the vertical lines, they don't meet at a point. They're not touching. And so then the question is, how did the artist determine the spacing between those lines? How is the spacing done? The lines are getting closer together as you go up the image, but by how much? There's no reference point to connect them all to. Yeah, so the first riddle is this question: how do you draw? How do you find the spacing for these horizontal lines? Okay, that's the question. So I'm gonna get rid of the art, and we'll just set this up more formally. Yeah, so in order to do this, you just start with two lines, and that the line at the top will be the horizon, and the bottom line is just maybe the bottom edge of your canvas. So what do? You pick a point on the horizon. That's called the vanishing point. And then on the edge of your canvas, you just use maybe a compass or a ruler to mark off evenly spaced points on the edge of your canvas. And then just connect them all to the vanishing point, and you'll get a depiction of these vertical lines which all converge off into the distance. Now, it's this kind of optical illusion thing. You have to trick your eyes because you might just see this as a tall pyramid, but what you have to do is see it as something that's going off, far off into the distance and getting smaller and converging off on the horizon. To make it clear the distinction, I also want to show you, or to have this kind of side by side with the view from above. So this is the bird's eye view. This is what you get if you're looking straight down from above at the path, and you can see that from the bird's eye view, all of the lines are parallel, but in perspective, they're all meeting. Okay, so now for the horizontal lines. The idea is that you have the choice for that first line, and that will determine the spacing. And why is that? Well, we know what to expect from the bird's eye view. If all of the lines, if all of the tiles on the ground are all the same tiles, then they should be evenly spaced. So the next row, should be just above. And so on. So it's no problem to draw in the bird's eye view. So the question is, where should that line be drawn in the perspective view? It turns out that it will look something like this, perspective. And the idea is that you actually don't get so much choice. You only get to choose the first spacing, and everything else should be forced because it's currently pointed above. And if you decided originally to choose a narrower spacing, you would get a picture of this. If instead you chose maybe a wider spacing, that would be the picture. Yes, the question is, what is this spacing? How am I doing this? I was able to animate these slides, but was I just guessing, trying to make it look good? You know, how did the artists from the Renaissance, how are they able to do this with accuracy? Now, maybe you would be able to work out mathematically. So if you sit down and you start doing some calculations, you might be able to work out something mathematical about the spacings. But I'm going to discourage that because the lines are getting very, very, very close. So even if you worked out the spacing between the lines at some number, you're going to have trouble at some point measuring, having a ruler that's accurate enough to make those very fine lines. So I'm going to sort of raise the stakes here, and instead of just saying, can you measure the lines, but actually find a way to construct this drawing without relying on a ruler or measurement. Something closer to a geometric construction where everything can be exact and not rely on you to approximate. Okay, so that's the setup. So how do you solve this? So I think what's best is just to simplify the setup here to the most essential information, which is just this. Instead of all the vertical lines, just two vertical lines, just the outer line. And they're meeting on the horizon, and then you choose the first space. And then, yeah, now that the picture is simplified, you can see that all you really get to work with is this trapezoid shape. That's all you've got. And you need to work out where should be the next horizontal line. Yeah, so I actually wanted to open this up and ask if you're having an intuition for a way to find the next line. Any thoughts? Ask the audience.
So the top vertical, the degree to which it decreases, ratio between the first top and the second top, should be the same ratio as the sides.
Okay, so Adam's suggesting something about keeping the ratios the same, something proportional. Charlie, were you going to say?
I was going to say make them similar.
Okay, make them similar. So same proportion.
Yeah.
It sounds like the same idea. Something like take this rectangle or take this trapezoid and scale it so that it's proportional. So on the computer, I just held shift while I scaled this, so that's really kept the proportions. And then just draw horizontal line across. Okay, it's very natural, right? Because you can do that again. Just take this trapezoid, scale it down proportionally, pick a line across, and then you just keep doing this. And here's the effect. Yep, it looks like a railroad, or for some kind of image like a railroad. The lines are getting closer together, which is good. And the other good news is that you can continue to do this and you'll never reach the top. Because the trapezoids are proportional, they're forming a geometric series, right? For those in the know. So you should be able to do this on and have no trouble. Yeah, so looks good to my eye. But is this what you would actually see if you looked at a railroad in real life? Well, what I'm going to do now is just take the camera and sort of tilt it up so you can see what it looks like from above. I'm going to tilt the camera here. Here it goes. Looking from above. And what do you think? How does it look? Okay, here. Let me add in some spacers. So these all have the same height. And yeah, not great, right? So, yeah, it turns out that the picture you get when you look from above, what we actually drew, is unevenly spaced. Let me bring back the perspective view. This is with similar trapezoids. And you can see that the squares are not lining up. So it turns out what you were the real spacing should actually look something more like this, a little more squished. Yeah, so actually these trapezoids are not all similar to each other. They're just getting thinner faster than they're getting narrower. So that's just surprising because it seemed like we picked the most natural thing to do, and it just didn't work. And I think that what we should take away from that is that we just have some kind of I don't know, we're misled somehow, or we have misconceptions about how things actually look in perspective. They might not look the way you were expecting. Okay, so what it really means is that we need a little bit, we need some more tools to figure out what's actually going on when you look at something in perspective. And it turns out there's an entire area of math that describes a setup like this. So what I want to do here is just motivate some sort of introduction to that area of math, which is called projective geometry. I just want to give you some of the motivation, like a short introduction, which will give us the tools to figure out what's actually going on in this picture. Okay, so the motivation starts out by asking questions about lines, and I think maybe some of my students are in the audience today, or maybe on Zoom, and so they'll know that if you connect or if you draw two lines, they meet at a point. Here are two more lines, they meet. But there's an exception to that rule, right? It's the parallel lines that don't meet at a point. And I don't know, you might find this to be just deeply unsatisfying that there's a rule that has exceptions like this. Two lines meet at a point unless they happen to be parallel lines, and this is a special edge case, and it's just upsetting. So maybe you decide that you want to change that and make a new kind of geometry or new kind of space where parallel lines meet somewhere. So we're going to force it our way. Okay, so here's what that looks like. We start with the plane, the ordinary thing. And to the plane, we're going to add this additional circle around the plane. This circle has the name, it's called the line of infinity. And it's supposed to be out at infinity, but then you wouldn't be able to see it. So in this model, I've just brought it in a little bit closer. So you can see the line of infinity. Okay, so what happens in this space? Well, if you have two lines like these, then they still meet at a point that has not changed. Okay, but what happens if instead the lines are parallel? Well, they don't meet in the ordinary plane. And so if we want them to meet, they have to meet somewhere not in the ordinary plane. And so what we'll do is introduce a new point on the line at infinity and just say they meet right there. So we're going to add a new point to the space that wasn't there before and just declare that those two parallel lines should meet right there. Okay, and so fixed. Now these parallel lines now meet at a point. And it's actually not just these parallel lines, but there's a whole family of parallel lines. All the parallel lines parallel to these lines also meet at that same point. So there's a point on the line of infinity corresponding to this family of parallel lines, and they're all meeting there. Okay. Now notice also the griffins themselves, like these vertical lines, they're also parallel. So they should also, we also want them to meet, and so we'll have a point on the line of infinity for them too. So every point on the line of infinity will correspond with a family like this of parallel lines that are all meeting now. Now you look at this and you might have some complaints. First, the lines, so I have to bend, so I'm making them bend at the top, which is also kind of unsatisfying because they're supposed to be straight lines. And the other complaint you might have is that the so-called line of infinity is a circle. It's not a line, and that's also concerning. And it turns out that both of those problems, I guess, with the model are just caused by the fact that I brought the line of infinity very close in. So let me now send it back all the way out to where it should be. And now the view looks like this. So you've got the plane, and the line of infinity is now far out. Now those lines aren't bent anymore, so that's good. But you can no longer see the line of infinity. And that's the case even if you sort of pan your view. Here, I'm going to move around a little bit. So you look and you look, and you just, no matter what you do, you can only see just a finite amount of the picture. Even if you move off for a million years, you still will never see the line of infinity. So if you want to see the line of infinity again, you have to do something special. You have to look up. So right now it's a bird's eye view, looking straight down. All you have to do now is just tilt your head and look off into the distance. So I'm going to do that now. I'm going to have the camera tilt up and look up, and aha. Now we're standing on a plane, looking out into the distance instead of down at your shoes. And hey, there's the line of infinity. So it's back. You can see it again. And hey, yeah, we can now see again the point where the point on the line of infinity where these parallel lines are meeting. That point is back in view. And hey, yeah, can you notice it? Does this look familiar to you? This picture? It's hopefully reminiscent of the picture we started with, the task, which is to draw this kind of grid in a perspective view. And so the artists in the Renaissance realized this. They realized that this kind of model that we just came up with, where you add points of infinity and make parallel lines meet, is actually a perfect model of how our vision works in 3D in perspective. They realized that actually when you stand on a grid and you look out to the horizon, that what you're actually seeing is something like this. It's exactly our model, where the line of infinity, the role of the line of infinity is played by the horizon. So it's the horizon that acts like a line of infinity. And you'll agree, it really does look like a line now. So that's good. It's kind of interesting. It's the thing where if you're standing out in the middle of nowhere, you can see the horizon all around you. And it looks like a line, but it's also somehow circular because you can sort of walk in a circle and see it all around you. But from this view, it really does look like a line. So that's how I get its name, that line of infinity. Yes, so here's the big insight. Once you realize that this really describes how we see in perspective, we get this phenomenon that families of parallel lines meet at a point on the horizon, because the horizon is the line of infinity. So parallel lines should meet. And then that's the big insight. So now that we know the model behind our perspective vision, we can make some more progress on the puzzle. Yeah, so remember that the goal was to figure out how to space the horizontal line. And here are the horizontal lines. So they're parallel, so they should meet on the horizon. The only problem is that from this view, they're actually parallel to the horizon. So they're parallel lines, but they're also parallel to the horizon. So while they do meet the horizon, it's just, you can't see it in this view. What you would have to do is, look to the, you would have to look to the right, and see where they're meeting the horizon over there at a point, and then connect them all up, and then tilt your head back. Unfortunately, you can't do that kind of tilting in a picture. You can't say like, look over here. I'm gonna find that point and connect them up and then just look back. You can't do that kind of tilting the camera in painting. So remarkably, the puzzle is still holding up on us. Because again, although these are supposed to meet somewhere on the horizon, we just can't see that point and we can't take advantage of it. So we just need to be a little bit more clever. And here's the trick. I'm gonna bring back a view of the new geometry we created, which, by the way, I didn't put it in the slides, but the idea of taking a space and adding points to infinity, more or less, is what you do in projective geometry. You would call this projective space. It's, of course, there are always nuances as with everything in that, but the idea of taking a space and adding points to infinity is kind of the idea behind projective geometry. So this is an example of a projective space. But anyway, here's the space, and maybe I can sort of hint at what's going to make this possible. I want to hint at you that there's actually a hidden family of parallel lines in this picture, if you can find it. If you just stare for a while. Any thoughts? Oh, okay. So we're only suggesting the diagonal lines, and that's great. I was trying to draw them in. Yeah, so actually the diagonal lines in this picture are also a family of parallel lines. So by the theory, they should all meet at a point on the line of infinity. And so this we can take advantage of to solve. This will solve the puzzle. Okay, you ready? Yeah, here's so this is a great insight, and here's how it works. Let's go all the way back to the original setup. You've got the vertical lines, and you've elected the spacing for the first pi, and you need to determine the rest of the lines. And here's the idea. I'm going to start by drawing in here in this bottom corner tile the diagonal that comes in. Now, take that diagonal line and extend it all the way to the line of the tree. Okay, good. Now look at this next box over and draw the diagonal. Okay, and now you just take your straight edge and very carefully extend this line, extend, and up. It meets, right? It meets the other line there on the horizon. And you do this again. So here, I'm drawing the other diagonal lines. Just take those and extend them all the way, and they all meet, just as the theory predicted they would. So it's beautiful, isn't it? There's no trickery here. This is really happening. If you do this for yourself, this will happen for you too. And in fact, I want you to focus now how to get to the next level. Just look at this point here in the far left corner. So that's the bottom left corner of one of the tiles. Now you don't know where is the top of that tile, so you can't just draw a little segment, but you know where the diagonal line should go if you extend it. So you'll have no trouble connecting the top point to that point, diagonal. And now you look in here and see where it meets. That should be the top right corner of that tile. So you get this new point here, which should be at the top of the next row of tiles. In fact, yeah, all of the intersection points there should be at the top of another tile, and wondrously, they're all collinear and lie on this horizontal line. It's amazing that it's working out, and you can keep doing this. So you have new diagonal line and slash and diagonal and across, and you just keep building out this picture. Isn't that beautiful? It's so clever, and it just looks really nice here. You can see that all the diagonal lines on the floor are all meeting on the horizon. And so that makes it possible. So here I'm going to hide the construction line so you can see the final picture. It's exact. No guesswork. Ta-da! Yes, so it's really nice. And just to wrap this one up, I think now with the understanding we have, we can address why the similar trapezoid strategy does not work. So here I'm going to just separate this out into the similar trapezoids. And because they're similar and their proportions are preserved, all of their diagonals should be parallel. The problem is you don't want them to be parallel from this view. They should be parallel when you look from above. So something's not quite right. Now, if you extend them all, they all hit different places. So in order to get the true perspective rendering, you want the trapezoids to be so that their diagonals meet at a point. So that way they're parallel from above, not parallel. Does that make sense? It's a little shift in perspective. Yeah, okay, so that's this riddle kind of in the books. But before we move away from this, it occurred to me that having made a slide with this imagery, that I've actually made some perspective graph paper, and I'm guessing that you've never had perspective graph paper before. So when you're in the presence of perspective graph paper, you should probably graph something and see how do graphs look. They could be really interesting. It turns out that when you graph things like lines and maybe like absolute value, they still look the same. So I'm going to prompt you with the interesting thing to graph, which is to graph the parabola y equals x squared. Why not? So here goes. Start by plotting the origin 0, 0. And then you get there's 1, 1 and minus 1, 1. And then here's 2, 4 and minus 2, 4. So looking pretty standard so far. You can keep going. Do you ever graph it like this where you go over 1, up 1, over 1, up 3, over 1, up 5, and you go over 1, up 7. And actually something interesting happens. So that's 4, 16. And I don't know if you can tell, but if you kind of squint and ignore the gray lines, it actually looks like when you go over 1 and up 7, this blue point is actually further inward than the point below it. I don't know if you see that. The points are actually going inward on each other. And as a matter of fact, if you plot all the points, you'll get an ellipse. Whoa, that's amazing. Yeah, what's going on here? This is just a cool effect. Now, if you actually were standing on a bunch of graph paper off to infinity, and you could just push a button that would light up a parabola on the floor, you would see, from your perspective, an ellipse. And it's actually tangent there to the line in infinity. Maybe the best way to think about what's happening here is just to remember that all of the vertical lines on the graph paper are not parallel from this view. They're all converging in. And when you draw a parabola, its ends start to look more and more like vertical lines. Don't you agree that the ends of the parabola start to look vertical? So they're starting to converge to look like the vertical lines, which all get brought into to that point on the horizon. So the ends actually get folded back in. Yeah, it's maybe not obvious why it should actually look like an ellipse instead of some other kind of folded shape. But maybe we can talk about that after. If you're curious, we can chat after the talk. But yeah, very nice. So sometimes these perspective graphs can give you some insight. In this case, insight on conic sections. Yeah, very nice. Okay, so I'm prepared now to, yeah, close this chapter and move on from this riddle and switch over to another. So, I don't really have a palette cleanser or anything, but maybe just kind of take a moment or kind of take a breath. I'm not sure. Yeah. Okay, so that's one down, and now let's talk about this other riddle that I actually brought for you. Okay. So in this second riddle, the setup is like this. Oh, and actually, I do have something I can say before starting this, which is that this riddle is classic, and has appeared in many books and puzzle collections. It's possible that you've heard this one before, which is okay. That would be good. So here's the setup. Imagine you're standing somewhere on Earth, holding a compass, and you walk this journey. You start by following the compass a mile to the south, and then you turn and follow the compass 1 mile to the east, and finally you walk with the compass 1 mile toward the north. And somehow, incredibly, you end up in exactly the same place as you started. And you just walked this path 1 mile north, a mile east, and then a mile, south, east, and then north. And in some miraculous way, you ended up exactly where you started, your home base or wherever you were. And so the question is, how is that possible? And if your first instinct is to say, well, maybe look at a map, then you'll get this feeling that it's just not possible wherever you put this little motif. It just doesn't make sense that you could start and end in the same place. And I agree. And that's why this riddle caught on, is because it's not clear right away that this should even be possible. Okay. But if instead of looking at the map, you look at an actual globe, then maybe after you kind of stand back and stare at the picture for a while and you think about walking this journey, you might have kind of a moment of insight on how this can be done. Yeah, maybe if you haven't already heard, if you don't already know this riddle, anyone kind of having like a tingling idea about where you could start your journey? Oh, the North Pole. The North Pole. Yeah, so if you were thinking the North Pole, then you're right. And here's, let me draw out what that journey looks like. You go a mile toward the South Pole. That's a large mile. Then you go a mile to the east. This is not the scale. And then you go 1 mile back north, and you get back where you started. So this really works. And so this is the proposed, the classical solution to this riddle. In the mathematical setting, it goes something like this, and the solution is it's the North Pole. By the way, has anyone heard this riddle before? Are you familiar before the talk? Wow. Okay, we have about 10 people. Okay, so I was hoping that if you've already heard the riddle before, that I could surprise you by informing you that there's actually another solution to this riddle. That's not the North Pole. Are you intrigued? I was hoping that maybe this is new to you. Yes, but so I'm promising that there's actually somewhere else on the globe, not the North Pole, where you can, honest to goodness, walk this 3-leg path and then the back where you started. It's probably not South Carolina. I, for one, have never walked in a U shape and ended up back where I started. But that's just me, and maybe it's somewhere else. But this is just this. And even with this promise of another solution, the fact that there is a solution at all just points out that there's something very counterintuitive about maps, because it really didn't seem possible when we were just looking at the map that this could be done at all. So either we have some kind of misconception or misunderstanding about the way that maps work. So it's going to even get close to answering this next question about more solutions. we can at least try to understand even the North Pole as a solution by taking some more time to understand maps. I'm going to make this map bigger. Yeah. So the two features of the map, the grid lines that I drew over top, you may know that the vertical lines are called lines of longitude, and the horizontal lines are called lines of latitude. And the surprising thing that only occurred to me really when I started thinking more deeply about this riddle is that maybe I've been misleading myself because it turns out that lines of latitude actually are not lines. They're not lines on the globe. And what I mean by that is if you want to walk along a line of latitude, you actually have to walk in not a straight line. And I don't think that's totally clear right away. It's possible that you had this sense by looking at a map that the lines of longitude and latitude play similar roles to each other. They're just directions you can walk in. But what I'm trying to highlight here is that they're actually fundamentally different in the sense that the lines of latitude actually are not straight paths when you're walking. But to really appreciate that, you have to understand a little bit more about the geometry of walking on the globe. Okay, so this gives us a reason to think a little bit more about the spherical geometry, the geometry of being on the surface of a sphere. Yeah, so let's talk a little bit more about it. And the first goal is to try to explain this, why lines of latitude are not straight lines. Yeah, so it turns out that the effects are most extreme toward the North Pole. So to really get a clear sense of what's going on, to make it most pronounced, we should put ourselves close to the North Pole. But before we look at that view, yeah, I inserted this. I wanted to make a comment about what it really means to walk east to west, to walk along the latitude line. And what it means is if you're really walking due east, then no component of your direction should be to the north. You shouldn't be getting any further north. And likewise, there should be no component of your movement to the south, away from the North Pole. In other words, maybe a new way to think about walking east should be you think about just keeping a fixed distance from the North Pole. You don't get any closer, and you don't get any further. It's a nice way to rethink what it means to walk east. And with that in mind, let's take a view where we're closer to the North Pole. So here you are, and there's the North Pole. I'm going to mark the North Pole with a candy stripe ball. And when you're standing near the pole and you want to walk east, the goal is to keep a fixed distance from the North Pole. And one way to do that is just to tie yourself with a rope to the North Pole. And then when you want to walk east, you just start walking where you keep the rope taut. That way you aren't getting any further north or any further away. And you just keep walking like this, and you'll end up walking in a circle. That's a circle. That you can have this experience of putting down a pole and walking. It certainly doesn't feel like walking in a straight line, but that's what it looks like to go east. That's east. That's walking due east. This is so boggling to me. I don't know why it never occurred to me that when you go to walk east, you're actually doing a circular movement. Is that strange? Is it just me? Maybe it's just me. Like, I thought was totally but it's accurate, and the analogy still holds up more or less when you're at a further place from the North Pole. Just imagine yourself kind of rappelling down the side of the Earth, and you're just going to still walk in a circle. It's just a bigger circle, but it's still this kind of circular path. So you can't just walk in a straight line. You have to be kind of curving, even if it's ever so slight. You know, these larger circles will have less curvature, so it's less pronounced, and you might not even be able to tell that you're walking in a circle. And on the scale of 1 mile from South Carolina, you're pretty much walking. For all intents and purposes, you're walking in a straight line. But on a global scale, these lines of latitude are really circular paths. So that's the first shock, I guess, about what makes the maps so misleading. Let me see if I bring back the, oh, yes, right. So what makes my original drawing misleading is that I drew all three stretches of the journey as straight lines. But now we're appreciating that the journey east is actually a circular, you walk along a circular arc. So that allows you to have a picture more like this, where you walk. The experience you have of walking is like walking straight away from the North Pole. Like you're letting out your rope until the rope is a mile long. And that's just a straight walk. And then you make this kind of arc path. And then you collect your rope and walk back to the North Pole. And so you really can have this kind of journey where you walk those three legs and end up back where you started. It's just my first picture that was U-shaped was a little bit misleading because that middle part of the journey can actually be, or is actually part of the circle. So there you go. Yeah, so that's the first. That's why now I think now we appreciate why the North Pole is a solution to this. Let's see. Yeah, so I think I have to try to remember what comes after this blank slide. Oh yes, okay. So coming back around. Yeah, here's that first solution. I just wanted to point out that when you actually put this little motif up at the top of the map here, it really is working. It seemed impossible at first on the map, but this does work because actually the entire top edge of the map corresponds with that single point, the North Pole. It's just a consequence of this map making. So this does work, but you put the motif anywhere else and it seems to fail. And so now let's come back to this question. I promised another solution. So how could there be another solution? Well, we've already taken advantage of the fact that the lines of latitude are not straight lines. But there's actually something else that's misleading about them. So here on the map, the lines of longitude stretch all the way across the map. And they do the same thing on the globe. They wrap all the way around the globe. But when you make this comparison side by side, you notice that there's something very different about the circles on the globe, which is that they have different lengths. They're not all the same length. You have these really small lines of latitude near the North Pole, and then they start to get longer as you work your way toward the equator. So the lines of latitude, not only are they not straight lines like the map leads you to believe, but they're also, the map makes them all look the same length, and they're not. There are lines of latitude that are shorter or longer than others. And it turns out we can leverage that fact to find more solutions to the puzzle. Yeah, so how does it work? If you want to find more solutions, you actually have to take yourself to the South Pole. Okay, so it's upside down. Here you are. In the South Pole, I wasn't exactly sure how to mark the South Pole, so here's a penguin. So how do you find another solution to this riddle? Well, here's the trick. You just want to find a line of longitude, one of those maybe we call them circles of longitude. We find one of these lines of longitude that is so close to the South Pole that it's actually very short.
You mean latitude?
Oh, did I say longitude? I meant latitude. Yeah. So you find one of these latitude lines that's so close to the pole that's actually really, really short. How short? Exactly 1 mile around. Were you thinking that? You can actually make this part of your journey. So the idea is you should start 1 mile north of that and just pick somewhere to start, like maybe here. And here's what your journey looks like. You walk 1 mile south, so you walk toward the South Pole, land on that circle. And now your eastward journey, you start walking this way. And as you travel east, your 1 mile journey will take you right back to where you started, right back to that point. And now you make the final trip 1 mile north, and you just repeat the path you already walked, and you're back where you started. So here's another solution to the riddle. Just take advantage of the fact that there are these really small lines of latitude near the South Pole. So actually, all the points on the gray, all those points are also solutions. So you get, we have the North Pole as a solution, and all of these points, which are 1 mile north of the 1 mile loop. So actually, there are infinitely many solutions to this puzzle, or to this riddle. So it's very nice. Any more solutions?
Yes,
Did we get them all?
we got some more.
There's more.
Yeah.
Okay, I was hoping to maybe surprise you one more time by saying that there are actually more solutions to this riddle. We're not done. But where could you possibly stand? We've already got the North Pole, and we figured out what to do with that. You take advantage of that 1 mile circuit, right? What else could you possibly do? Well, here's what you can do. Let's go back to the South Pole. You have this. You can imagine there's like a circular track of the South Pole. It's kind of like 1 mile loop. Maybe there's also one that's shorter track. How short? Exactly. Yeah, that's right. Exactly half a mile. Yeah, there's also a half-mile track. Maybe you don't have as much endurance. Yeah. So what can you do with a half-mile track? Well, start a mile north, right? And pick somewhere to start here, and your journey looks like this. You walk down to that half-mile track, and then your mile east means you actually walk around twice. You make 2 laps on the half-mile track, right? And then again, you're back here, and then make the journey north. So you actually you can walk the half-mile track twice and make 2 laps. So all these gray dash points are also solutions to the riddle. And why stop at the half-mile track? What about a third of a mile track, right? Quarter mile? It's kind of like 1 over n, 1/10 of a mile. You'll just lap that track n times. So actually, there are not just these solutions, but let's also get the mile above the half-mile loop, mile above the third of a mile loop, mile above the quarter mile loop, and so you get all of these other. So there not only are there infinitely many solutions, there's this infinite family of infinitely many solutions. All these places stand, plus the North Pole. But these are nice. The sort of the separation here is that we're taking advantage of these 2 different properties of the lines of latitude, that they're curved near the North Pole side, and that they can be as short as you want. Yeah, that's very nice. Yeah, I'm hoping that if you had already heard the riddle and you know about the North Pole, you can add this to your repertoire when you share riddles with someone. You might surprise them with these bonus solutions. Okay, I think yeah, I had this here. I was going to point out that the lines of latitude are just so misleading because yes, they're not straight, and they're not straight paths, and they're not the same length. But this claim I'm making that they're circular paths, I think this is the only thing that really requires a little bit more. It's just a little bit more subtle, because when you walk this path, so remember you lead yourself to the North Pole and you walk in a circle, you might have this concern that are you really walking in a circle? Because you know the Earth, so the surface of the Earth is rounded, and so maybe you are walking straight. It's just that the rounding of the Earth is so what I'm pointing out here is that there's actually a sort of a subtlety to what it means to walk in a straight line versus a circle. And if you want to be a little bit more rigorous, one way to do it is you want to like take these lines of latitude and see what it really feels like to walk on the path. We will really only understand it if it's flattened out. We have experiences of walking on staying flat. So if you want to do the flattening out, it's notoriously difficult to flatten out the surface of the sphere. But one way you can make progress is to find these surfaces that are like tangent to the, or just approximating the Earth's surface, right on that line of latitude. So imagine here I found a cone that's just touching the surface of the, or just sort of grazing past the line of latitude. And they sort of locally are near the line of latitude, the surfaces are very similar. So you can think of a little band, just a band, a conic band just around that line of latitude, which is more or less an approximation of the Earth's surface there. And then these other lines of latitude, sometimes that approximating comes a little steeper, and on the equator, it's not a cone at all. It's a cylinder, which is kind of like a special cone, right? It's like the parabola of. Right? So you just take these objects that are a little easier to work with, and you just have to cut them open. You can flatten them out, and you can see that sometimes the path that you were walking is actually like you're walking along a circular arc, and the further down the Earth you are, it really is kind of a more gradual, softer path. And in this special case, when you're on the equator, you just cut open the cylinder and unravel it, and find out that you're actually walking in a straight line. This kind of reasoning requires just a little bit more care, but I just want to give you the impression of how you can, or a sense of how it works to figure out the real experience of walking those paths. So when you walk one of those paths, you have the experience of walking this path. It always feels flat to you, but somehow the fact that the Earth is curved is adding some extra curvature to these, which will complete the circles. Yeah, so if you're interested in some of the details on it, how you can actually figure out what it means to talk about walking a path and the experience of walking a path, we can chat after the talk. But that's wraps up this riddle. Yeah, that was 2 riddles. I hope you enjoyed. Thank you.
The equator is the only line of latitude that is a great circle, right? Like all longitude lines are great circles, right? That, sort of a circle that cuts the sphere in half, right?
That's right. So if you're thinking about this, the cylinder corresponding to those straight line paths, then it really is the equators or the great circles, right? Which are straight paths, and you're right. So all of the lines of longitude are like equators, and so when you walk north to south, you really are walking a straight line. And maybe the intuition here is that when you're following a compass and you walk north, you move north, the North Pole stays still in front of you, and so you don't have to change course. But when you walk east, the North Pole moves, so your compass will move too, and it's the east to west journey that requires you to keep correcting yourself. But the north-south journey, you really can just walk straight toward the North Pole or away.
And so if you do stereographic projection, right, the latitude lines turn into circles. The longitude lines are lines,
Oh, yeah,
right?
right. Yes, that's right.
Any questions, comments?
So that had me curious about what would happen if you walked a mile along a great circle and then walked a mile along a great circle at right angles and then walked a line along the great circle back towards the north. Where would you end up?
That's a great question. The question is, what happens if instead of walking due east, you just figure out which direction is east before you start walking, throw in your compass and just walk straight in that direction, and ignore the fact that you're veering off course to the east. That's a nice question. Yeah, can you end up back where you started? The answer might be no.
Well, if you walk more than a mile.
It might depend on the size of the earth. Yeah. I can
Okay.
certainly
be careful with your future questions. I do not want the Flat Earth Society trolling my YouTube page. So, because that's what's next.
What if we make the earth flat?
Well, flat earth theory is actually our simple.
You know, it's yours really the ditch with the boundary identified, what if we unidentified?
Well, the physics of a flat earth are actually somewhat similar to what you were talking about at the beginning, with limits points at infinity, because that's how gravity would have to work essentially in their theory of a flat earth. That the edge of the earth, essentially they act like points at infinity, where gravity becomes like, it goes off to infinity. It doesn't make sense, of course, because like, this is how they try to reconcile their theory, is kind of by introducing the edge of their world as like points at infinity that you can't reach. And you can look up this stuff, and I won't say.
Well, most of the modern theories, and I use this rather loosely, involve Antarctica being a wall of ice that holds the ocean.
Yeah.
These are people that have watched way too much Game of Thrones.
Go by vote.
And they love the
Right.
Yes, yes, the royal family is there on the yeah.
I've never actually said.
Other questions before we completely pervert us off? Okay, let's thank him again.
Oh, hello, Ryan. My mom's a situation.
A flat earth what?
Flat earther.
They don't want you to get.
No, okay. He was like, no, it's round.